counting. Oops, there's an echo. Maybe someone. Okay, so counting periodic orbits of one-dimensional maps, the third lecture. Okay, so I wanted to maybe start with reminding you a bit of the prime number theorem from number theory. Okay, and so this is a result where we want to somehow count prime numbers up to a certain cutoff. So we introduce this prime counting function.
Yeah, I'm looking for that.
So
No.
this function phi, capital Phi, defined for some x, some positive x, to be the number primes e that are less than or equal than x. And the content of the prime number theorem is that the function grows like x over log x. In the sense that the quotient between these two converges to 1 as x goes to infinity. All right, so that's the content of the prime number theorem, and this is saying basically that well, this prime number function is roughly like x over log x for large values of x. Or you could also interpret this as follows: if you take some large x, and you want to pick an integer at random between 1 and x, then the probability that that integer is a prime number is roughly equal to 1 over log of x, because that's the content of the prime number theorem. Okay, so so what I want to talk today is one of many possible versions of this result that hold for dynamical systems. Now, so like I think maybe Wednesday, we want to count periodic points with a certain weight, and the weight that we want to choose is this geometric potential. Okay, but let me first state the analogous version of this in the case of rational map. So let's fix a complex rational map acting on the Riemann sphere. And I want to assume here that the degree is at least 2. And I want to introduce a bunch of notation, so I'll fix a periodic point. So T is going to be a periodic point. All right, so I think we already introduced the notation pi of P as the minimal period P. So P could have several periods if you count the orbit twice or times and so on. So this will be the minimal period. P, as before, P had the orbit. And these are the objects that we want to count. So this will play the role of prime numbers. And the weight will be the norm of the multiplier. Which is also the product of the derivative over the points in curve. Okay. Now it's convenient to talk only about orbits. So I want to introduce, make the notation only depend on the orbit. So the pi hat will be just pi of t. Same for the weight, so the norm of the multiplier, and as before, this will be the notation for the orbits of it, the set of orbits of periodic. All right, so as in the case of the prime number theorem, we want to introduce a function that will count periodic points according to its weight, the specific weight. So let's introduce the reason of lambda. And so as before, we're counting the number of, well, in this situation, it will be periodic orbits of F of size bounded by lambda, the cutoff that we have chosen. And the theorem says that we have a similar type of counting, but this will only hold under certain assumption on F. So maybe I need to introduce a hypothesis. We are going to say that so F is uniformly hyperbolic of periodic orbits. If there is some lambda not bigger than 1, so that the multipliers grow exponentially, at least like lambda, so that for every periodic orbit, the norm of the multiplier is at least lambda to the minimum period. Okay. In other words, the multipliers grow exponentially with the period. So of course, if a function is uniformly expanding on the Julia set, so if every derivative grows exponentially, this is automatically satisfied. But we will only need the growth on the periodic cycles. Okay. All right, so the theorem is with and myself. Okay, so we take F as before. So uniformly hyperbolic. The orbit. And we need to exclude a few cases where it's relatively easy to see that the conclusion is false. So, so we assume that F is not conjugate to a monomial or a predicate polynomial or a lattice map. So these are somehow the standard exceptional cases in many theorems, and this is another case where we need to exclude them. Yeah.
So, in particular, F cannot have attracting or parabolic periodic points, right?
Okay, yes. Good point. Yeah, so we can restrict here to this requirement for p hat repelling. So we only need this bound when p hat is repelling. Now, so we are allowing and attracting cycles.
Not parabolic.
Right. So though this is a condition on repelling cycles, it implies that there are no neutral cycles. Okay. Right. So formally, it's I mean, it looks like we allow parabolic cycles, but actually not. Okay. But what's important is that we do want to allow attracting cycles because this includes the uniformly hyperbolic case where you need some attractors to have uniform hyperbolicity.
Should there be a log there in the definition of lambda? No.
No log.
Does it exclude parabolic?
This condition excludes the neutral points. Yes.
Okay.
Yeah. Okay. So.
Right. There would be some and long time.
That's not completely obvious for Kremer.
I say
Yeah. Okay. Right.
repelling space,
Lot of time close.
All right. So maybe let me just. So let me at least finish the statement that we can discuss. All right. So the conclusion is that so if we write delta for the upper dimension of the Julia set, we have a similar statement. So the prime orbit counting function is asymptotic to. We need to make a correction here. And instead of writing just plain lambda, we need lambda to the delta. That's the right. And this converges to delta. Okay, so that's the theorem. All right, so here I need to say, okay, so I mean, okay, you could prefer maybe to divide by delta. In that case, we have a delta here. That's another, and perhaps it looks slightly more similar to the previous statement. So it depends on how you want to write it, but. Okay, so maybe let me make some remarks here. So in the case where f is uniformly hyperbolic, this is the result first shown by O and Winter. Now, there are some interesting features of this theorem. So they actually show an even more precise version where you have a power savings error term. And there's a quite interesting version where you also take into account the arguments of the repelling periodic points that show some type of equidistribution in terms of the angles. So they also hold in this case, but I just don't want to discuss that. Let me ignore that, though that's kind of big part of this theorem. And for axiom A, this is diffeomorphisms. This is a theorem by Ariel-Policot. But okay, so this is 90 maybe. And there's a long story. Okay, I mean, this started with the geodesic flow on a compact Riemann surface where you count periodic orbits according to their length. That's somehow closer to the Artin-Mazur story. So instead of house of dimension, you see the entropy appearing. There were several important refinements by Margulis in his thesis, and then Tarnack studied the case of finite area, I mean, with cusps in particular. He studied that for the modular curve, so there are a bunch of number theoretical applications of this theorem. And again, I mean, there's another big story about the error term that was done by Policot and Sharp based on the work of Lodbrok-Yat, blah, blah, blah. Okay, so there's a lot of, yeah.
So can you just remind me then the difference between yours and in terms of the uniform hyperbolicity standard? Yes.
Yeah, so they require uniform hyperbolicity everywhere on the Julia set in particular. Right, so uniform expansion on the whole Julia set. So there are no critical points that, as we will see.
And yours is really weaker. I mean, there are examples.
Right. Okay. Yeah. So let's check the hypothesis. So in the case of, well, so this is equivalent to so the uniform hyperbolicity on the orbits. That's equivalent to the topological Collegman condition introduced by Felix. And in the case of, say, quadratic maps where there's only one critical point, this is also equivalent to the Collegman condition, and there are results by Benedict Carleson and then refined by Avila and Moreira, where they show that based on work of Lubitsch, where they show that for almost every parameter is either hyperbolic, uniformly hyperbolic, so as in the theorem of Owen-Winter, or satisfies this uniform hyperbolicity in periodic orbits, this Collegman condition. And in the quadratic family, so we know that there is a set of positive measure of parameters where this is satisfied, and yet the uniform hyperbolicity fails. Okay, so there are some significant, it's a significant set of maps that satisfies this condition. Right. Yeah, so now the proof somehow, so I wanted to mention, first I want to, yeah. Yeah, okay, so, okay, so it won't be relevant, okay, but this exponential growth of derivatives on the critical value. Okay. All right, so maybe this is just like, I really want to concentrate on at least some of the ideas in the proof. There's a long story that I'm skipping in both in the general case and in dimension one. All right, so let me just mention that the proof, somehow this condition appeared, we use it crucially at least 2 times, and it seems a bit difficult to go beyond. But I think an interesting test case would be this Fibonacci map that was studied by Lubitsch and Milnor. So I would be very interested in knowing. So maybe let me write here. Big problem. So, so that's the completion hold. Or the Fibonacci. Now, so this is a quadratic map that you can define more or less as the map where the closest returns to the critical point are given by the Fibonacci numbers. Okay, so that's the definition of the Fibonacci map. And in some sense, this is the, at least from a combinatorial point of view, this is the most recurrent that you can get. So the fastest that you can approach the critical point is through these Fibonacci numbers.
Come on.
Sorry?
It's a revised book. Doesn't?
Yeah, okay. Maybe. No, but it's close to it. So the derivative doesn't grow exponentially, but it grows like super polynomially. I think it's n to the log n. That's results of Lubitsch and Milnor. Right, so Lubitsch and Milnor proved that this is in fact quite expanding. It has an absolutely continuous invariant measure. Yeah.
So, you mean these maps are recurrent in particular?
Yes, this map is recurrent, and it's not renormalizable. It's not renormalizable, and the critical point returns, at least from a combinatorial point of view, it returns as fast as possible. But it turns out that somehow unexpectedly, this is very close to being this non-uniformly expanding in a strong way, right? So this would be like a natural candidate to test whether such a result can hold.
Do you know any parameter C's of that d square plus C is Fibonacci quadratic?
Yeah. There's a unique such point. You can define it through, for example, its needing sequence. There's an explicit way to define it. It involves, I mean, the definition involves some Fibonacci numbers. This is studied in a paper by Lubitsch and Milnor. There's a nice description.
Are there numerical estimates to see how this ratio behaves to the Fibonacci map?
No, actually I would be very interested in knowing. I thought about this for some time, and I changed my mind from one day to the next whether it was true or not, and I just couldn't decide, and I just have no idea.
Does it stand for harmonic?
I haven't thought about that seriously, but as we will see, even the convergence of the zeta function is unclear. I mean, it's not obvious at least. Yeah, that's a good point. So maybe take the cauliflower, so C plus C squared, for example. That would be an interesting case too. Okay. Now, if we go all the way to something that is really, really far from being non-uniformly hyperbolic, something like the Feigenbaum map. So let's take, say, the quadratic map that has the Feigenbaum combinatorics. So it's a fixed point of renormalization for period 2. Now, this means that basically, so we have an interval that has this interval that comes back to itself after 2 iterations. And the restriction to this interval J conjugate to the map itself, right? So we have this renormalization. So it's a renormalization almost fixed point. I'm not claiming that here that the conjugacy is affine, but there's a nice map that conjugates both. But we would, so you can repeat this procedure indefinitely. So the renormalization will be renormalizable period 2, and its renormalization is conjugate to the original map. And so you can repeat and repeat and repeat. And well, Sullivan showed that, in fact, the renormalizations converge to some limit, to some limit unimodal map, and the convergence is in fact in the C1 category. Okay, so this is a long story just to say that, well, this means that the small maps or the small Julia sets look very like a certain limit. Now, this limit, say, has a fixed point alpha. And this fixed point alpha has a certain multiplier. So all of this is to say that the original map F will have a periodic point, period 2 to the n, which is a fixed point for the nth renormalization. And since the convergence is in the class C1, the multipliers of these periodic points of period n converge to the multiplier at alpha. So you have infinitely many cycles that have abounded, so that their multipliers converge. So they're actually bounded, right? So that means that so all of this is just to say that in this particular case, the quadratic map with the Feigenbaum combinatorics, there is a certain cutoff lambda naught. So this is already infinite numbers. We reach infinity in finite time, in some sense. So there is no way that anything like this will hold.
This is df infinity.
Sorry? The
Df infinity of alpha infinity.
oh yes, thank you. Yes. Okay, so all right, so this is a kind of a bit like extreme. Might be possible to have easier counter examples, but so some type of non-uniform hyperbolicity is needed. Okay, that's the message here. So we cannot expect this to hold always, at least in this form. Yeah.
But why is the same argument doesn't work for the Fibonacci quadratic map? Because it's multiple in general sets.
Right. So that's an interesting point. So the deformation space of the fixed point is one-dimensional, and there is this decay of geometry. Okay, so the nth normalization is really expanding. So that's really what's behind the work of Leibovitz and Milnor, and that's why this map is so expanding. Okay, so you get some. So the next generalized renormalization is really way more expanding than the previous one. Yeah.
But if you take degree greater than 2, for instance, z power c or plus c.
Right, exactly. So I think at least as soon as you go to, I think it's beyond 2, right? For real, in the real case, you have bounded geometry, and in that case, you have the same picture. Yeah, that's a good point. Yeah. So here, so it's crucial in my question here that we're taking the quadratic polynomial with the Fibonacci. I wouldn't expect. I mean, the same reasoning would show that already, say in the cubic case, this will fit.
It seems plausible that we take the Johnson, Kuchenheimer type examples, it will also be infinite. So, or at least it will grow faster than would in the uniformly hyperbolic set.
Yeah, that's a good question, but I guess your earlier question should be answered first. I mean,
well, the parabolic point only creates one. It creates fewer problems than an almost parabolic Like,
Well, these parabolic cascades, they're approaching parabolic points, right? So that's the point.
Yes.
Yeah. So if it's already false for parabolics, I would expect maybe also this is false for the.
I would imagine it could be true for parabolic and false for.
Okay, yeah,
Others.
yes. Yeah, so there are lots of questions. Okay, all right. Okay, so that's the theorem, and I wanted to discuss a bit the what are the ingredients in the proof. So let's go back to the Ruelle zeta function. Oh, yeah. Before that, so let me mention some of the ingredients in the proof of the prime number theorem, at least the classical proof. So in the proof of the prime number theorem, so there are several elements that are important here. One is that the Riemann zeta function. So I'm discussing the classical proof by Hadamard and de la Vallée involving the Riemann zeta function. Okay. So here, so one of the ingredients is that the Riemann zeta function has a metamorphic extension to the whole plane. Now, this extension has a unique pole at 1, and this pole is simple. In some sense, that's responsible for the main growth, main term. And the other ingredient here is that there are no zeros of real particles. Okay, so if you combine, so these are the about 3 main elements, and you combine these with the Euler product, which somehow connect the analytic side of the Riemann zeta function we're discussing here with the arithmetics of numbers, of integers, and what's called the Tauberian theorem in industry. They yield the prime number. So, at least from the analytic side, those are the main 3 statements. Now, the proof for this prime orbit theorem is similar. The strategy, at least the main strategy. Now, there's a separate question of how you prove the analog statements. So, similar. So similar. Strategy where instead of dealing with the Riemann zeta function, we're going to use this Ruelle zeta function that we saw on Wednesday. So we define as before, Tn best as the sum over the periodic points here then of lambda p to the minus s. So here, this is the same as what I wrote on Wednesday, except that we are now taking the potential phi to be minus log of the normal. Okay. So the so-called geometric potential. So the Ruelle zeta function for the geometric potential is then defined as 4 and we have this Euler type product that for this potential here, it reads as follows: this Ruelle zeta function is equal to the product over periodic orbits. So now we change from periodic points here to periodic orbits here, and we need to multiply 1 over 1 minus lambda p to the minus s. Okay, so that's the Euler type product, and the somehow analog version is really the main part of this theorem. So the main theorem here would be following. So we take f as before. And we can say that the Ruelle zeta function extends to a non-vanishing metamorphic function on a neighborhood of the half plane with the real part of least delta. So here we have the x-plane. Delta is the Hausdorff dimension, and what I'm saying here is that there's an extension to some neighborhood of this closed half plane to the right. Okay. There's a unique pole at s equal to delta, and this pole is simple. Okay, so is more or less analogous to this three statement here. The difference is that we don't have, and I don't know if it's true, whether you can have a meromorphic extension to the whole plane. The extension here is only on some neighborhood of this right half plane, and that's sufficient to apply this Tauberian theorem. Okay, so there's nothing really I can say that, I mean, once you reach this stage, it's just copy and paste from the prime number theorem. It's exactly the same. There's really no, I mean, you're better off reading any book on any of the proofs. The prime number theorem is exactly the same part. Okay, so I want to discuss the proof of this part. Right? Yeah, so maybe it's good time to break. Good. All right, so I wanted to discuss the remaining time, some of the elements that go into the proof of this result, and in fact, this a lot of this goes back to the work of Ruelle and Polycott, actually. All right, so as we did on Wednesday, so the first question is convergence. So, I mean, can we tell, like for the Riemann-Zeta function, once you have the series, the definition of the Riemann-Zeta function, you can more or less easily see that it converges on the open right plane with real part 1, okay, real part bigger than 1. So similarly here, we can try to see what's the, I mean, the easiest convergence result that you can get. And let me make an observation here. So we have this partition type function. And when S is real, then I'm going to denote by T. This is a real number. Real and positive, actually. And in fact, the imaginary part only contributes with a number of norm 1. So you get essentially the same up to a different argument in each term. So we have this easy bound where the norm of this partition function is at most the n of the real part. Okay. So this leads to this, so if we want to analyze the convergence of the Ruelle set of functions, you remember that the Ruelle set of function is defined this way. The root test would be to compute this number that we introduce at the pressure on periodic points. Seems so. And goes to infinity of 1 over n log. Yeah. Right, so now in the uniformly hyperbolic case, so let's suppose for a minute that f is uniformly hyperbolic. In this situation, this way of computing the pressure using periodic points is in fact equal to the usual topological pressure for the geometric potential. the main point here is that there are no critical points on the Julia set, so this geometric potential is in a bounded function and actually Holder continuous. So we are in the very standard theory of the thermodynamic formalism, okay? And the math is uniformly hyperbolic, so you have shadowing and other techniques that lead to these maybe very good way. So these two coincide, and then we have Bowen's formula. That basically says that the topological pressure is strictly decreasing, and for the geometric potential, it vanishes precisely at the Hausdorff dimension of the Julia set. Well, what we call delta. Right? So if we combine this with the root test, this is saying precisely the analogous statement for us in the Riemann zeta function that the Ruelle zeta function converges locally uniformly on the right half plane with real parts, at least delta, this is delta. So from Bowen's, so in the uniformly hyperbolic setting, from Bowen's formula, we can deduce that the natural domain of convergence is this right half plane. So all the work is to extend this statement to the line with real part equal to delta. So the challenge is then to show that at each of these points there is a holomorphic extension that doesn't vanish, and that at delta there is a meromorphic extension with a simple pole at delta. Okay. That's the okay. So let's see what happens for a general. So for a general rational map, there is, I mean, it's not so convenient to work with the topological pressure due to the fact that there might be critical points in the Julia set. Nevertheless, there's this very general theorem by Felix that, in fact, for every rational map, you can define some version of the pressure function that is well behaved. So we define the geometric pressure function using the variational principle, so it's the supremum of the free energy, the invariant probability, So Felix proved that this function is convex, non-increasing, finite. And being finite and convex implies that, in fact, this Lipschitz continuous. So it's regular. It's non-increasing and vanishes at, so the first zero, sorry, let me write it this way. So the first zero is the hyperbolic dimension of the Julia set. Now, this is not quite the Hauser dimension of the Julia set. This is the supremum of hyperbolic, uniformly hyperbolic sets contained in the Julia set. Okay. So now I was careful here, and I didn't write strictly increasing because that's not true. So what happens that in many cases, say if there's a parabolic point, the pressure function will touch the x-axis and it will vanish from there on. This is bad news for the root test, right? For the root test, at least the easy thing would be to have something negative here that would ensure the local uniform convergence. Okay. So this is a possible scenario. Okay. Now, there's another issue here that, well, this is not quite what we need. We need here the pressure function computed on periodic points. Now, Felix, Stas, and I studied this problem, and there are like 6 or 7, I forgot, different natural versions of pressure that you could study, and they all agree, except for one inequality that I don't know, I think we don't know how to prove, and this is precisely the inequality we would need here. So let me explain that. So this is a very frustrating problem that I want to discuss. So what we know is that the pressure on periodic points is larger than or equal than this pressure. So let me perhaps spend some time on discussing why something like this would make sense. So, for example, so open problem, so prove so we don't know whether for a general rational map we have equality. So in fact, it's conceivable. This is what I don't know how to rule out. It may happen that there is a even worse case scenario where we would have a rational function for which the pressure computed on periodic orbit never vanishes. Right? I don't know how to rule that out. Do you know how to? Yeah, so that's so in principle, we wouldn't even know whether the pressure vanishes at the hyperbolic dimension. All right, so the idea is some type of shadowing. So first, I think Felix also showed that when you compute the periodic orbit on pre-images, we do have the same result as using the variational principle. Okay, so at least in the negative spectrum, yeah. All right, so this is saying that if we, in other words, you want a formula that's the limit when n goes to infinity of 1/n log. So here, instead of using periodic points like here, so we have the same type of limit, except that we replace this partition function computed on periodic points by the same type of sum where we use nth pre-images of a reference point. Now, I'm exaggerating here. This is false if you choose an arbitrary x. However, if you throw out some small set, some thin set of dimension 0, we do have this equality. All right, so this is just some shadowing identity argument where we pick some base point x, and whenever we have a cycle, at least if the cycle is sufficiently repelling, you can find basically a pre-image that will shadow this periodic orbit, right? Wait, this is the other way around. Sorry, that's for the no, sorry. So this is the argument to show the argument that you would use to show the reverse inequality that we don't know how to show. Sorry. So, okay. So basically, we know that the right pressure, in some sense, is given by the computation of this partition function on pre-images. And we would like to show that that's bounded by the that bounds the pressure computed on periodic orbits. So the argument you would use is okay. So you take a periodic orbit, and provided that the periodic orbit was sufficiently expanding, you can find an iterated pre-image that shadows the periodic orbit. So you pick up the pressure, the contribution of this periodic orbit with an iterated pre-image. Now the danger, and this is the part we don't know how to do here to have the equality, is that you could have the following situation. So this is the situation we don't know how to rule out. So it could happen that maybe you have a packet of periodic points of period n, all of which are very weak. So have a very weak multipliers, and they travel more or less together. So concretely, we show that if the inequality fails, in fact, there would be for arbitrarily large n, so the period n, there would be an exponentially large number of periodic points of period n, all of which are exponentially close, and so that their multipliers are exponentially close to 1. So this seems very unlikely. So we have this theorem by Fatou, right, to the Fatou-Shishikura inequality that tells you that there are at most a finite number of parabolic cycles. This is saying that somehow we have an exponentially large number of cycles that are very, very close to being parabolic. They're repelling.
In fact, Kramer.
Yeah. Okay.
So it is known that I'm very close to Kramer periodic orbit. There are periodic orbits of arbitrarily long. And complete the not that they just visited. This is possible, but it's not known how many.
Mhm. Right. So some quantitative version of the Fatou-Shishikura inequality would be sufficient to rule out this case. Okay. Well, have any ideas? I would be really, really interested. Okay, so this is at least one point where you need to somehow use some stronger hypothesis. So you just let F be an arbitrary reference map, even for the convergence of the zeta function, and we're not even discussing whether there are zeros or there's a simple pole. Just for the convergence on the open half plane, there's an issue, right? So what we do know is that with a mild, so this is easy to rule out, with a mild non-uniform hyperbolicity condition, and in particular, if the rational map satisfies this periodic, uniform hyperbolicity on periodic orbits, then we can rule this possibility, and these two pressures actually agree. Yeah.
So if the picture is like that, then it's zero after a while, so then you cannot conclude the convergence.
Yeah, even in that case, so if there is a parabolic point, for example, the pressure is zero, and just from this analysis, from the root test, you cannot say anything. It's inconclusive. Yeah.
And is P pair always convex and increasing anyways?
Yes. Yes, it is. Yeah.
And could
Finite.
do they coincide for like, I don't know, T very negatives?
It's a good question.
Is the pressure and the pressure on periodic points, do they coincide for T very, very negative, very small?
I think they might coincide up to a certain point. Yeah.
T methods.
I don't know. I don't know. All right, so maybe let me
What? I wonder, can you prove your theorem for all the cases when you know the identity of periodic pressure and usual pressure, or you still need something more? You need.
yeah, I'll comment on this. Yeah.
Okay.
So let me state something and then. Okay, so this is told by Felix. So if F is uniformly hyperbolic. On periodic orbits. Then we actually have equality, and this pressure function is strictly decreasing. And vanishes precisely at them. So this is analogous to the hyperbolic situation where the pressure function is strictly decreasing and will vanish precisely at delta. So, and it's in fact stronger than that. So what we know is that this is optimal. So if F is a rational map that is not uniformly hyperbolic on periodic orbits, we have this picture here. So it's, the pressure function will be flat. It doesn't go beyond, it doesn't have negative values at all. Okay. So even for the convergence, to deduce convergence from the properties of the pressure function, so if you want to use the root test, we are already restricted to this case here. So even going beyond that, slightly beyond that, you need to work even to for the convergence of the Ruelle function.
And there we have identity for all t raised to equal to 0 or negative 2.
Yeah, in all of the real line.
Oh,
Yeah, they agree in all of the real line. Right. So, well, as I mentioned, this condition is equivalent to the topological Collegman condition, which is also in turn equivalent to the exponential shrinking of components. So this rules out this easily, right? So if you take a ball and you look at the nth pre-image, it will decrease exponentially fast. Here, this the multipliers here are close to 1, it's sub-exponential. So these balls here are sub-exponentially large, right? It's not compatible with the exponential shrinking of components. Now, so perhaps the next step is to show that there is a simple pole delta at the Hausdorff dimension, and this is related to this Ruelle-Perot-Frobenius theorem. So we already know that we have convergence to the right of delta. And so let's discuss next the simple pole at delta. We have this Ruelle-Frobenius. Theorem. So that, let's say that F is uniformly hyperbolic. And let's introduce this operator, the transfer operator. So we take some function psi, and this operator maps this function to the following: you sum over the images. So we sum the values of the function over the preimages, and we weight according to the clear cut. So the Ruelle parameter theorem is saying that this function grows when we apply this function to say 1. This converges uniformly. Yeah, maybe we need to let's take real compute. Perhaps write it this way. So first there is an eigenvalue of, or an eigenfunction of eigenvalue the exponential of pressure, and we have this convergence towards the eigenvalue. So iterate any function, say in particular 1, this converges to only C1 to its eigenfunction. Now, the point here is that we want to, again, we want to approximate the partition function, which is computed on periodic points, with the analogous function, but computed on preimages of a reference point x. The sum over there. Okay, and this is precisely, so if you unravel the definition here, this is precisely iterating the transfer operator n times applied to the constant function equal to 1 and evaluated at x. Okay. Now, if we look at the expression for the Ruelle zeta function, what does it mean to have a simple pole? It means the following. So if we multiply the Ruelle zeta function by 1 minus s, sorry, delta minus s, we should have some function which is holomorphic on a neighborhood of delta. So let's write delta minus s as minus log delta minus s. So that's minute. Yeah, I think it's slightly better to write it this way. So let's compute. I guess, sorry. Okay, sorry, I blanked there. Okay, so let me just say that having simple pole at S equal to delta is equivalent to showing that this grows exponentially like
using plus, right?
yes. Yeah, but this is the complex variable and all right, so we want to one minute. Right, so we want right, so we want this to be roughly like the exponential of n. Right, and we want these to be smaller little pole of yeah. Right, so basically, okay, sorry. So this is equivalent, in fact, to it converging exponentially with it. Okay, so I mean, just writing what it means for the Ruelle zeta function to have a simple pole and delta, together with the fact that this grows exponentially with the pressure function. That's what we did before. Having a simple pole translates into showing that we have this exponential error term, right? So we want this to converge exponentially to one as n goes to infinity. Now, so this is essentially, I mean, if we were computing this partition function in terms of the iterated preimages, this would be exactly the content of the Ruelle-Perron-Frobenius theorem. So the Ruelle-Perron-Frobenius theorem says that so if we evaluate this function at any point, it will converge to some number, right? And the exponential convergence here is, sorry, the convergence here is exponential. So, okay, so in the classical setting, we are in the uniformly hyperbolic case, okay, where we are letting the transfer operator act on the space of Holder continuous potentials. And the exponential convergence here happens for the Holder norm, but in fact, we only need to show that there is a simple pole, we just need the usual, the uniform norm to converge here. There.
Quite interesting question. Yeah. When to go to perturbation. Like when you did not necessarily set. So here you're acting just on the constant functions, is it correct?
Sorry, say that
You're
again?
just taking constant functions.
Yeah.
Correct?
Right. So so there's a spectral gap. Okay. So this exponential of the pressure is a simple eigenvalue, and there's a spectral gap, and from the spectral gap you have this exponential convergence to the. And this happens for every Holder function, except that if you take a different one, you need to add a constant.
Does the spectral gap not actually cancel which space you're considering you are greater?
Right. So as I said, Holder continuous potentials.
We have no general.
So this is for uniformly hyperbolic maps.
Even such.
Yeah. Okay.
Yes.
All right. So basically, here the problem is to extend this for maps that are uniformly hyperbolic compatible points. So now, well, basically here. Suppose now F is uniformly hyperbolic. Now, the main issue is, of course, that we may have critical points in the Julia set, right? So and well, I think there are this early work of Smirnov where he studied the transfer operator of the rational map on directly on some Banach spaces. But that's only for values of E which are negative. Here we need some positive values. And well, so to the best of my knowledge, so that's maybe a question for Fabrizio, whether can you actually study directly? So is there some Banach space where you could let the transfer operator act and have, you know, spectral gap and so on. So I don't know how to do that. So the replacement is the inducing scheme, which I just don't think I have enough time to. So I can say at least something. So we have this inducing scheme. So the idea is to basically partition the dynamics into two different parts. Okay, so two independent systems in some sense. There's one where so the issue is the critical points. So we may, you know, have a couple of critical points, and well, the rough idea is that we want to maybe be happy and take those sets that never approach any of the critical points. Okay. So you choose, I mean, you need to be a bit careful. I mean, this is perhaps the whole point. But if for a well-chosen neighborhood of the critical set, okay, so it's the union of sets around critical points. You can consider the set of points that never enter this neighborhood. So maybe points in the Julia set that never enter this neighborhood B. And this is at least for under this assumption, in good cases, it's a uniformly expanding set. So in principle, we may apply all of the previous theory, and we have estimates and so on. But crucially here, the Hausdorff dimension of this set is strictly smaller than the. So you don't even need to show some type of prime number theorem for that hyperbolic set. You just need a simple estimate showing that if you count the periodic points that are here, so those that never enter a neighborhood of the critical set, they're relatively small in comparison to the expected number. Okay, so a simple estimate suffices here. Actually, it's enough. Actually, what we know is that the upper box dimension is, even the upper box dimension is smaller, and that's sufficient to exclude that. So the upshot, of course, I don't have time, but basically, you can consider a return map to have, so you have some type of return map. And this return map is uniform methodology. All right. Well, can't really say much more. All right. So basically, so let me just say that you can basically repeat all of the estimates as in the hyperbolic case. You need some extra care because here this map has infinitely many branches, so you need to be slightly careful, but we have some good estimates. For example, we know that if you take into account the time with respect to the original map, this map is uniformly expanding. Okay. So it's a uniformly expanding map, and it's hyperbolic, so you can repeat all the previous story. And let me finish with this. So there's a drawback here, which is the following. So here, to get this uniform hyperbolicity, we are forced to draw certain orbits. So there are orbits that do return here, so they visit this neighborhood of the critical point, but when they return, they have the orbit is not uniformly expanding. This happens. Okay, and this is perhaps another source where we use these hypotheses. There is a combinatorial estimate that tells you that the number of those periodic orbits that are in this limbo, they're not here, so they do approach, but they don't have sufficient expansion to appear in the induced map, those periodic orbits are sub-exponentially numbered, meaning that we can show that they grow out at most like a small exponential by taking these components small. Okay, so using the fact that the map is uniformly hyperbolic on periodic orbits, and together with the fact that you have a sub-exponential number of them, you can show that they don't contribute to the counting in a significant way. Okay. So that's another point. So this is, for example, where for the Fibonacci map, it looks tricky to. So even you have a nice map. There is a nice inducing scheme. However, it seems, at least I had difficulties in estimating the contribution of those periodic orbits that are in this limbo. They're not in the hyperbolic set, and they're not in this map. All right, thank you for your attention.
Juan, are there any questions? Okay, I'll start with, does it carry over to the usual setting? Is there any function?
Yeah, I didn't even mention that. Yeah, yeah, that's true. So all of this applies to interval maps. Yeah.
Sure.
Parallel.
This is a question, is there any? No.
So for the prime orbit theorem, so the prime orbit theorem holds for uniformly hyperbolic. So for maps that are uniformly hyperbolic and periodic orbits for interval maps.
Any other questions?
I just said that everyone asked the question during the talk. No one waits for the end.
Okay, so shall we thank Juan for a wonderful mini course?
Yep.